Our first speaker to the stage. Please join me in welcoming Chua. His talk is titled The Multiverse of Ecosystem Valuation.
My name is Louis. Good evening, everyone. Hi.
Hi.
Really bright. I can't
It's
see
very
anything.
bright. Yeah. Cannot see past the lights.
So the title of my talk today is The Multiverse of Ecosystem Valuation. I'll take this down. So why multiverse? So when I embarked on this project, when I embarked on kind of thinking about how do I represent my project, I thought, well, nobody's going to really want to think about economics, national accounting. These are technically pretty boring subjects. So I thought, well, actually, it is a multiverse, right? Because we're exploring things that could have but didn't happen. We're exploring some of the preferences of people or things that cannot speak, and of things that are not yet born. So this is kind of how I want to frame valuation. And what's in a price? Price doesn't have to be money. Price is always relative. It's always a trade-off. So think of you paying for something and then purchasing something. That means you can't have the money to buy something else. Or spending your time doing something means you don't have the time to do something else, right? It's always a trade-off. It's always relative. So the price you pay really reflects what you would otherwise do in a parallel, almost counterfactual world. And this is what a lot of economists call opportunity costs. There's the mic working. So these are costs of these counterfactual worlds. You can think of them that way. And really it's a function of your imagination. So that's like your mind-blown meme GIF over there. So this is why, I titled the talk Multiverse of Valuation. But what are we really talking about? Okay, so the background is across the world, globally, we're embarking on this natural capital accounting project. And this isn't just a United States thing. It isn't just a Hawaii thing. It's a global thing. And what this does is it expands what we call a system of national accounting. And this SNA, if you see in that tiny box in the lower right-hand corner, that spits out your GDP every year. And if you see over there, it's probably too small. But if you can see those rows, it's log timber, furniture. So say, for example, a logging company earns 50 units of money. And then the furniture, is consumed for 80 credits. So your total GDP is 80, whether that's 50 plus 30 or 80, that is the GDP totaled up. So that's kind of value added 30 plus 50, which is, taken from the logging company. What we're trying to do is expand that to incorporate some of the ecosystem services that go into that logging, right? So when you extract resources, that may come at a cost. So we say, when we expand that, we say the ecosystem contributes 30. And if you add them up, there's still 80, but then at that point, you're actually incorporating a lot of what the ecosystems contribute to your economy. So even though the GDP doesn't change, you have that additional row for forests. So this is universe number one, right? This is the current way of doing things. If we expand the universe even more, this is universe number two, we add an additional row that isn't technically monetized in a lot of situations. This can be stuff like air filtration or shade that forests provide. So these are also ecosystem services, but they don't generally have a price, right? We don't usually trade them off, or we don't think of them relatively whenever we make purchases or make decisions, everyday decisions. So now you can see at the bottom right, the GDP now is 95, right? So in this universe, it's a larger universe that accounts for various trade-offs and changes in different parts of the non-market economy. So this is the ecosystem account, so SEAEA. So this incorporates intermediate as well as final ecosystem services. So what does this look like in Hawaii? In Hawaii, we right now we have a more cool level accounting. So instead of, looking at counties, looking at census tracts, we're thinking of, shaking things up a little bit. Why don't we go back to what the Hawaiians used to account for, consumption and services. Let's look at the Moku level. So that's kind of what we're kind of pushing towards. And we're accounting for ecosystem contributions to our economy with significant caveats and limitations, just to add that. So these are kind of what it looks like. This is the Waianae Moku in Oahu. If you know Oahu, this is Waianae on the west side of Oahu. And they're generally congruent with watersheds, and they extend into the near shore coastal ecosystems as well. So this is something peculiar and particular to Hawaii. So the thing about accounting for them is you have to look at extent. So these are geographical scope, the extent of the ecosystems as they change year to year, right? Because when we look at GDP, a lot of things change year to year. The conditions change as well, the services change as well as the asset changes. So we can really go crazy with the condition indicators. It's data, more data. So think Aupua, so much data then can go into informing the condition that happens across the Aupua. So this is from Mauka in the mountains all the way to Makai in the sea. So all these indicators, for example, your bleaching hotspots, and these are marine ones. And if you look at 1985, temperatures were far lower than they are in September this last year. So it's about 2 degrees Celsius higher. And in 2016, where there was a marine heat wave, you could see even then temperatures weren't really as high as compared to now. So we're really, in uncharted waters, so to speak. Coral cover, for example, and if you can see the tiny little moku slivers around the coast, that's the kind of marine moku. So that's kind of few of the data sets that we look at. So we have all these extending the universe, but is it good enough? Well, actually, it's broken, right? The prices aren't great mechanisms for a suboptimal world. In conventional classical economics, it assumes an optimal world. So it assumes prices are truly relative when they're not. Are we playing economic Jenga? Are we just extracting things until things start to fall apart? There's also the question of whether should we monetize things, because ecological opportunity costs are really severely underestimated if you don't monetize them. But then if you do monetize them, that means people assume then that's it, right? There's no more to it. So generally, we struggle to see the larger and longer picture in terms of time frame, in terms of hundreds of years instead of, maybe looking at 2 to 5 year cycles. What is the true price? Maybe we'll never know what the true price is, but we have what in ecology is a precautionary principle, and economists have the idea of path dependency, which is going down the path and making it so costly to switch paths, or you can think of it as jumping across the universe, that no one ever really does it because you go down this path of no return. So the true takeaway is ecosystem accounting, valuation, it really helps us get closer to arriving at the true ecological price of our decisions. And if you want to scan this QR code, I have an app over there that has a beta app that tells you different kind of ecosystem extents across Hawaii. So go ahead and do that. Give you some time. Any takers? No? Just oh, sorry. You good? Awesome. Don't want to guilt trip you guys into doing this, but it's great. It's pretty good. I did it. Yeah, get in touch. Thank you very much. Mahalo. And I hope you enjoy the rest of your night. Are there any questions?
Yeah, you got to stay here for questions. Questions for Louis. Ooh, George, what is your question?
You know, when you mentioned lots of problem issues, but I haven't researched about solutions that say, for instance, being a monetary thing and an unmonetary thing, how do you merge the two? Because we know that the world is more holistic than that. So how do we merge monetary system with an unmonetary?
And please repeat the question.
So the question from Uncle over there is, how do we merge, there's a lot of things that cannot be monetized, right? Is that your question? And how do we merge the non-monetary kind of values with some of the monetary values that are captured by the market economy? Is that your question? I think that's the sort of question that keeps me up at night. It's so insurmountable, it's almost impossible to do. They're these two very, very different worlds, and I can talk for 4 hours about this, right? Because it's underpinned by different worldviews and, expectations of what can be quantified, can be commodified. But the short answer to your question is keep in contact, get in touch with me. I can tell you more. It's difficult. The way I do it is try to find a bridge. So if something is non-monetizable, how much do people value it in terms of time spent, for example? So there are creative ways to get around it. How much community voluntary hours are there in that location on that specific ecosystem service or asset? That's one way you could go about it. You could also quantify the avoided costs. You could quantify things like real estate values around a specific ecosystem asset that you think is really valuable. And those prices, it's capitalized in real estate prices. So those houses that are near, beautiful beaches, beautiful parks, they're actually a lot more expensive. And if you can tease them out using econometrics, you can actually get at some of the prices. But then again, it comes with a lot of caveats and limitations. So the short answer is we can talk some more if you're interested, but it's difficult. It's complicated. It depends.
Other questions for Louis? I have one. You showed us some maps of different moku in the Hawaiian Islands. What are some examples of different ecosystem services that you're digging into and trying to investigate the value of? Can you give us some examples?
So there's a couple of there's recreation. That's something that is easier to do because you can see people recreating. You can kind of track as well of social media with number of cars parked, for example, how busy places are, how many permits are bought. So that's an easy one. Coastal protection, sea level rise is a huge issue in Hawaii. So the costs of not having, reefs that buffer some of these sea level rise or storm surges, king tides, that also has a very legitimate costs, in terms of insuring your houses, properties. And the last one, I think, fisheries. We all love fish. We all love fishing, and we live off fish, as food, as recreation. We go fishing for fun as well. So that's something that our lab is really digging into. But personally, I'm super interested in cultural stuff because that goes into, the multiverse more so than other services, because you talk about intergenerational equity and intra-generational equity. So you're dealing in space, time, and a broader kind of remit. Yep.
Thank you to Louis. Big round of applause for Louis. Okay, I like this multiverse analogy, thinking about the people who are not yet born and intra-generational equity. That's very cool. Our next speaker is Patrick Nichols. His talk is titled, "Where's Waldo? Simplifying Detection of Nuisance Species." Let's give a big round of applause to Patrick.
right, thank you everyone for being here this evening. I appreciate it. Again, my name is Patrick Nichols. I'm the zoology PhD student at the University of Hawaii at Manoa. And again, tonight I'm going to be talking about a little bit of work I've been doing in the applied sciences, specifically making the management of nuisance species a little easier for the managers themselves. So first off, I just want to make sure everyone knows what I'm talking about when I mean a nuisance species. A nuisance species is basically anything that impacts the environment, usually in a negative way, something that humans are concerned with. Examples can be anything from land, animals, and plants. So you see here, yellow crazy ant is one example on Oahu that we have. And I'm really glad I'm following Louis' talk here because a recent assessment of nuisance species actually tried to put the value of them, the cost to manage them, at $424 billion per year. And that's expected to increase tenfold every decade. Another example would be cats. If you've seen the cats around campus, they are a nuisance species. We also have marine nuisance species. If you've heard of the lionfish, Indo-Pacific lionfish making its way into the Atlantic, the Caribbean. So I'm going to be looking at specifically a nuisance species found in Papahanaumokuakea Marine National Monument in the Northwest Hawaiian Islands, roughly 1,000 miles from here. So just in our backyard, but still very far away, very remote and very difficult to access. That also means it's very difficult for managers to detect these nuisance species and manage them effectively. So typically how one would go about looking at a reef and the nuisance species on a coral reef is you would put divers in the water, as you see here in the bottom corner of this picture. There's a tiny little diver going around and visually surveying the entire reef. And if they find any nuisance species, that would be a flag, and they would then hopefully invest time and more resources into actually managing. This is actually extremely difficult for Papahanaumokuakea because, again, it's one of the largest marine reserves in the entire world. It's roughly the same area as the entire country of Peru. So you can imagine swimming around, and that amount of water is just not quite feasible. Now, these more traditional visual survey methods work extremely well when the water is clear, calm, and shallow like this, and you see in this photo. But they don't do so well when access is really limiting. You can't put divers in the water, or in situations when you can't even see anything underwater. So that's kind of where my research comes in. But first, I'm going to talk a little bit more about the actual species that we're looking at. So this is a red algae that was discovered in 2016 in Papahanaumokuakea. It's called Chondria tumulosa. And it kind of startled researchers at first when it was discovered because it was found in these dense, thick mats, completely smothering the reef underneath. Furthermore, it was able to reproduce asexually through fragmentation. So just tiny pieces of this algae could be dislodged and form entire new thickets of the algae elsewhere. Even more than that, it's really easy to find Chondria tumulosa when it's in high abundance, as you see in the picture here on the right. But at certain sites, it was found down in less than 1% abundance. This tiny little fragment is one little piece of Chondria tumulosa growing underneath native algae. So if you're not trained in looking for this, it's very easy that you could miss it. So again, that's where I came in. I work with what's called environmental DNA, or eDNAs. That's DNA that all living things give off into the environment. And my research specifically focuses on reef organisms, where we filter out all the DNA from seawater samples, and we get everything from corals to algae, inverts, fishes. We also incidentally get all the nuisance species in these samples. So what I did was came up with a test that isolates Chondria tumulosa DNA from these samples, and we can determine whether or not it's present at our sites. So we did this across Papahanaumokuakea, starting originally at ground zero at Manavai, Pearl and Hermes Atoll. This is way up in the northwest corner of the Northwest Hawaiian Islands. So again, 1,000 miles away. And at the sites we sampled, we were able to accurately get from the eDNA the presence and absence of Chondria tumulosa when compared to the visual surveyors, the professionals doing the benthic surveys at these sites. A year later, it was found to have spread to Kauai or Midway Atoll. And again, we surveyed sites here and found the same thing, that the eDNA was accurately able to detect Chondria tumulosa. And this past year at Holaniku, it was found to have spread there as well, in the neighboring atoll. And then eDNA actually was able to detect Chondria tumulosa in extremely low abundance, less than 1%. So again, these little tiny fragments are giving off enough DNA that we can detect. We also decided to collect water samples from further down the atoll. So the Kapu and Lalo here are about halfway down the entire chain of the Hawaiian Islands. And while it wasn't detected, this actually serves as a baseline for potential future invasion. So again, Chondria tumulosa was not detected either visually or through the eDNA at these sites. And then finally, we decided to survey all the ports and harbors around Oahu to make sure that we weren't inadvertently bringing back Chondria tumulosa from the reserve. So we didn't have visual data from these sites, but the eDNA suggested that it indeed was not here. So while we don't know where it came from, we now have a good idea that it is contained in the upper 3 atolls in Papahanaumokuakea. So this test works extremely well just using surface collections of seawater, but that wasn't quite easy enough. The methods I've described have actually been implemented by Colt here in the room. Thanks for being here.
Yay.
Appreciate all your work. I'm sure he can attest to exactly how difficult this method is, having to be trained for hours on the use of this system, and then needing, all these pumps and filters and wires and electricity. It's not easy to do. Again, I wasn't there, but it actually required a whole entire makeshift lab space to be brought on board the ships going up to the reserve. Furthermore, again, all this equipment is extremely heavy, bulky, and doesn't make implementation in these remote areas easy. So what I decided to try instead was a new technique we call soaking, passive filtration, where we basically just collect the water in jugs, place the filters in the water, and then the DNA binds to the filters. So you don't need any of these bulky pumps. This minimizes the equipment needs, but it still requires bulky collections of water. So you're collecting gallons upon gallons of water. You need somewhere to go with that. And to save some time, I'm just going to say that that whole method didn't work. So we kind of scrapped that and went in a different direction. What we did instead was a technique called passive filtration, where we just place a filter into a tiny mesh cage, and I actually have one here just to show you how easy this is to make and implement. It's just a couple zip ties, mesh, and the filter. That's what I like to call the filter package. This minimizes the equipment needs, requires no bulky collections of water, and it's extremely easy to use. Anybody could make this little package here and just drop it into the water and retrieve it later. So we decided to test that in Papahanaumokuakea, and we're actually able to detect presence or absence just by placing this little filter thing in the water for 15 minutes at each site. Now, this is extremely important because, again, a lot of these operations are done from these little boats, where it's extremely easy to drop something in the water and go do your work for 15 minutes, where we can't really have the filters on board and there's no electricity and all that. This is a great way to circumvent. It's also really important because in places like Honolulu Harbor, where we cannot see the bottom and see what's there, we can easily drop something into the water and detect whether or not the DNA is present. It's also extremely important because there's certain places where you cannot actually access getting into the water and collecting all the water. So again, we are working with deploying these little packages all over the islands and all over Papahanaumokuakea to continue monitoring the spread of this nuisance species. So I believe that's all I have for today, and I'd like to specifically thank Colt, who did a lot of the actual field work on this, and everyone else who was involved at NOAA, DAR, Fish and Wildlife Services, etc. Thank you. Wow.
I love it. Questions for Patrick? Ooh. Let's start with Cindy and then we'll go to Sean. Cindy, what's your question?
Mentioned in your first slide that it was 424 billion, but what geographic area is that cover? Is that US or?
That's globally.
Please repeat the
Yeah, so
question.
the question was, the valuation was $427 billion, nuisance species. So yeah, that's a global valuation of nuisance species. So it's just a fraction of that for Hawaii. But again, we're one of the most prone places to having nuisance species come in. So yeah, it's definitely relevant here.
How much water do you think passes over that filter in 15 minutes?
So yeah, the question is, how much water do you think passes over the filter in 15 minutes? We have no idea. So that's why it works so well though. And it didn't work when we put it in the little containers of water because we think the volume of water just wasn't enough. That was roughly a gallon of water that we would drop the filter into and kind of shake it around and see what it does. That didn't work. So we were like, okay, it has to be in the water column. It has to be exposed to the waves and the swell, all of that, the currents. So while we don't know how much water is in contact, we do know that standardized 15-minute soaking at all these sites did work. So it's more about this time. Yeah.
I have a question from the biosecurity aspect. A lot of these vessels dock in Honolulu before they hop on the port. Yeah, so a big protocol that the monument does is checking every vessel, doing all inspections. But a lot of this is human led and has room for, I guess, inaccuracy. So I guess how acute is that filter in terms of would it be effective in serving as a secondary step for biosecurity, kind of like pre-checks for hulls? For example, like if there was chondria, a fistful in a propeller or something, would that filter be able to pick it up, or does it have a threshold of it needs to be a 2 foot by 2 foot patch in 1 mile of water for it to be effective?
Gotcha. Yeah, good question. So the question is basically, can this be used as a way to assist the biomonitoring at these ports and harbors? And how much chondria needs to be present in order for it to be detected on the filters? Is that correct? Good enough. So yeah, again, we haven't actually quantified specifically, but we have modeled kind of the trade-off between how much chondria is present at these sites and the depth of the site, which gives us an idea of how close we need the filter to be. And to detect it down to less than 1% abundance, so this is extremely small fraction, you need to be relatively within 2 meters of the chondria at less than 1% abundance. You can be much further away if there's much more chondria. That's kind of how the relationship works. So if you're expecting it to be an extremely low abundance, yeah, the closer the better, or the longer the better. If you let that filter kind of sit there, you're more likely to detect it.
I have a question, Patrick.
Okay.
I have 2 questions. First question, how many Waldos are in your presentation?
2. Well, two different ones, yeah.
2 Waldos, I saw one. Okay. Second question. You talked about testing a new method that ended up failing. What is that like as a scientist? Can you talk about risk and failure in the work of a scientist?
Yeah, great question. It doesn't feel good. Luckily, that wasn't the first thing we tested. The first thing we tested was the active filtration, which worked beautifully. Again, that's not always the case, but it is probably frustrating when something doesn't work. Not necessarily for me, but again, there's a lot of people behind this project, specifically that project, that collected the water and spent time soaking them for different, lengths of time. We did up to 12 hours. So, on their already very busy schedule. in a very remote location trying to do this project for me. And then I have to report back and say, I'm sorry, that didn't work. So yeah, it's tough, but then we shifted gears and we figured out something that does work probably better and makes everyone's lives easier. So hope to see that continue.
That's excellent. Okay, thank you. Big round of applause for Patrick. That's a great lesson for all of us. You got to take risks and figure out what works and what doesn't. Thanks, Patrick. Before I bring our third and final speaker to the stage, let's do the raffle. And how this is going to work is Heather's going to shake up the basket, shake it up, and she's going to pull out the lucky ticket, and all of you are going to pull out your tickets. And we will read off the last 3 numbers on the ticket. If you are the lucky winner, you can come visit us at the Sea Grant table and we will give you a Sea Grant t-shirt. We have all the sizes. Here we go. Drum roll, please. Is our lucky winner. Okay. Come visit us at the Sea Grant table and we will give you a t-shirt. Awesome. If you want a t-shirt, come next week in person. We'll do the raffle again. Let's bring our third speaker to the stage. Our third speaker is Sean Swift. His talk is titled, "Does this soup look healthy? Ocean Chemistry off the coast of Lahaina."
Okay, hello everybody. My name is Sean Swift, PhD student in marine biology at UH Manuel. And I'm actually really happy to be following Patrick's talk because I'm also going to be talking about the ocean and all the crazy stuff that we can find in there, but more from like a chemistry perspective. So I'm going to start by talking about soup, which for me is like, it's like a helpful way to think about what's going on in terms of ocean chemistry. So the ocean is basically a kind of soup, right? It's got all the right ingredients. It's got plants, it's got animals, and it has a sort of broth. And I think it's useful to think about ocean water as a broth because if you think about soup broths, there's all different kinds, and it's this kind of complex merging of all of the ingredients that went into that soup, and there could be a lot, right? It's a complicated chemical mixture. And we often look at ocean water and we're like, oh yeah, it's just water, it's there. But there's actually a lot going on in there chemically. So let's run through a little hypothetical here. This is you, you're encountering a new soup for the first time in the wild. And somebody's gonna ask you to describe this soup later, okay? They're gonna be like, what was it like? Tell me everything about this soup. So how are you gonna do that? You're gonna trust your senses, right? So the first thing we can do, we can touch the soup. We can put our finger in there and figure out how deep it is, or what the temperature is, or if it's moving or not. And these are great first steps to do with any soup, right? You want to know if it's coming at you. You want to know if it's moving around. And if you're really sensitive, maybe you got some shark genes or something, and you can sense the electric currents going through the soup. And that can tell you a lot, actually. You can learn about the saltiness, or the acidity, or even the oxygen levels inside of the soup. And so as researchers, instead of touching things, we're using sensors and probes. So I think of these as my little fingers that I can put out into something like a soup, and I can figure out some of these physical parameters of what's going on. But it's not going to really tell me like what kind of soup this is, right? I still don't know very much about it. So the next thing we can do is we can see the soup. We can get eyes on the soup. It's important. We can see colors. And as researchers, we have access to really nice equipment that lets us see a lot of different colors. So we can see into the ultraviolet range. And we can put numbers on everything. We can say at this wavelength of light, it's this much, and over here, it's this much. And this can give us kind of like a profile of what we think is going on chemically. We don't know for sure, but we're like, oh, this soup is red, maybe it's a tomato soup. Gets us started. The next thing we could do is we could smell the soup. And I'm sure you all know what soups smell like. There's some really pungent ones out there. Maybe you're smelling something like garlic, or something really peppery, or maybe you're smelling something bad, like somebody burned the soup, or maybe it's old, maybe it's kind of rotten. And so this is really getting at what's going on chemically in that soup. And so we have a piece of equipment called a gas chromatograph, which you actually evaporate chemical compounds out of the soup, and we can figure out which ones they are. And that will tell us, what's going on with these volatile organic compounds. So the last thing we would do is we taste the soup. And this is probably the most important thing that you'd want to describe to someone, right? So what does it taste like? Because this is where all the stuff that is actually in that liquid is living, right? So dissolved organic compounds, things like fats and sugars, but also maybe things that we don't really want to be eating, like plastics or pesticides or pharmaceutical products or all kinds of things. We have another fancy piece of equipment called liquid chromatography that can tell us what kinds of chemicals like that are in our soup. We can also figure out if the soup is carbonated. I mean, it's kind of unusual for soups, but there's probably some carbon dioxide in there, or maybe it's got some alkalinity, and this can tell us about how it could resist being acidified. This is really more pertaining to oceans, but we're sticking with soup for now. We can also taste metals, so you could think of that metallic taste in your mouth, something like iron. But there's also other metals that we might be concerned about, things like arsenic or lead, which hopefully nobody knows what that tastes like. But if we did taste that, it would be a really bad sign. We wouldn't want to share this soup with anyone. And the last thing we want to know is what kind of microbes are in our soup. And this is because the microbes, they can change all of these other parameters, right? They're a living part of what's in here. If you think of some of the great flavors of the world, like kimchi or miso soup or shoyu, this is very Asian heavy, but these are all microbial flavors, right? And so we have to pay attention to the microbes, and we do that by sequencing their DNA, much like Patrick was talking about with sequencing algae. And so basically, we are applying all of our senses to understand what's going on in a liquid, and that could be a soup or it could be the ocean. And that's kind of how I think about our approach to understanding water quality. So when do we need to know what's in our water, right? Unfortunately, it's usually when something bad happens, like a pollution event or there's some challenge where we need to use all of this, frankly, very expensive and labor-intensive equipment, and we have to put it all together to confront some really bad thing that's happening. So sometimes I think about it kind of like this. I think of it like a giant Gundam of fancy scientific equipment that we're putting together to understand some problem. And so what are some water quality problems that we face? Things like wastewater. And so this is a picture of the wastewater injection well at Kahikili in West Maui. This is an oil spill. So this is Deepwater Horizon in the Gulf of Mexico. Or groundwater contamination. So in our lab, we worked on looking at what happens when jet fuel gets into groundwater and how microbes start to change that fuel and turn it into different kinds of chemical compounds. And the last thing is fire, right? So this is a picture of the Thomas fire, which burned about almost 300,000 acres in Southern California and made this huge plume of ash that went out into the ocean and altered ocean chemistry. And so in our state, obviously the most recent bad thing to happen was the Lahaina wildfire. And, with the fire, it was this huge tragedy, right? And people's minds don't necessarily go straight to thinking about water quality, particularly ocean water quality. But the way I think about Lahaina, and I grew up on Maui, and I spent a lot of time in Lahaina, is it's a very ocean-focused town, right? So you can see there's like this barrier reef that goes around the whole town. It makes for good surf breaks. It makes for good fish habitat. It protects the beaches where people take their kids. So yeah, I spent a lot of time there as a kid, and I just think, when I think about Lahaina, I think about water quality and ocean activities. So luckily, I'm at the University of Hawaii in the marine biology program, and so I could join this team of experts. People like Andrea Kealoha over here. So she lives on Maui. She's from Maui. She's a faculty in oceanography, and she's an expert in reef metabolism. Or Nick Hako, he does metals in the ocean. And Craig Nelson, who's my advisor, he does organic compounds and microbes. And Eileen Alley, who works for Sea Grant. studies contaminants. And then also all my fellow students like Joel and Justin, Sky and Peter, we all got together and we were like, okay, we can do something about this, and we can try to answer some questions about what's going on in the water off of Lahaina. So the first thing we did was we wanted to ask some questions about how contaminants might be moving offshore. This is a big concern for residents on Lanai. So we did a transect. We started off in Lahaina Harbor up there, and we went to 5 sites about a mile apart, getting almost halfway to Lanai and collecting water samples at each site. And for each water sample, we're running all of the same analyses that I mentioned before when I was talking about soup. And then for shoreline sampling, this is where we're getting into questions about like how might runoff affect these near shore areas, beaches that people will probably be returning to pretty soon. They're reopening sections of Lahaina for residents to return, and folks are pretty connected to the ocean, so they're gonna want to know if they can go back into this water. And so these are 3 pictures from the same site actually. So this is where you park right on Front Street, and you can see there's just like utter devastation there. And then it's a short walk to the beach, which is now blackened with ash. And the last thing we're going to do is we're looking at reef metabolism. This is trying to understand how the reef is responding to all these stressors. And we can do this with our little sensors and our fancy machines. And we can see how the reef is breathing. We can look at its respiration, and we can see if it's growing or shrinking based on carbonate chemistry. You can see if it's building more structure, or if maybe it's starting to go away. And so this will all have a big impact on the future of Lahaina and how we interact with the ocean there. And so I just want to finish off by saying, mahalo to everybody on this team who's been working their butts off, trying to do all this stuff. And Patrick was talking about what happens with the fear of failure. I mean, the pressure is really on for this project, right? But I ultimately just feel so grateful to be a part of Sea Grant and a part of UH Manoa, and in a place where we have access to these resources and this amazing equipment and experts who can do all this kind of stuff. I just really appreciate all of that, and I appreciate you all for coming out and listening and getting educated about this stuff too. So thank you. Have a good night.
Questions for Sean? I can't see some people. Are there like hands up that I can't see? Okay, let's go Patrick. And then if you have a hand up and I can't see you, just say something.
Where does the data from this end up?
Yeah, so that's a great question. That's something we're trying to figure out. We're probably going to be working with Pacayus. They have this amazing online data visualization extravaganza that everybody should check out. Lori knows all about it. You can ask her. And we're also putting together a community-facing kind of website where we're trying to share. There's a lot of other groups in Lahaina that are producing data about contamination or about other things. And we're trying to share all of that publicly as fast as we can.
I see hands up. I think back there, it's like a cloud.
Okay, I was making sure that when you guys have a question. What are your plans to, if there are any, to continue these into the future in terms of the sampling? Like, are you going to go back at regular intervals and try to look at the same sites to see how it's changing over time?
Yeah. So
Can you repeat the question,
yeah.
please, Sean? Thank you.
Repeating for people online, the question was, how are we going to repeat the sampling, or how are we going to continue this into the future? So currently, this project was funded by the National Science Foundation as a RAPID grant. So that's a 1-year funding. I think we're also going to be getting some funding through HIEMA, through the emergency management agencies, to continue this work. But right now, our main focus is on understanding what it looks like right now and what it looks like after the next really big rainfall. So Lahaina's on the west side, it's very dry. There hasn't been any big rainstorms. And so everybody's very concerned about what's going to happen when there's a big rainstorm and a lot of runoff. But there's basically a lot of people want this to continue. And so we don't have plans yet, but we're hoping to continue long term.
George, did you have a question? And then we'll go to Darren next.
Yeah, I thought in a fact, just one shot chance at all the way from shoreline to things. I was wondering if there's a reason for that, because with the currents and everything, it's offshore environmental shifts, right? So
Yes, it does. Yeah, so if you really wanted to understand what was going on in the channel, like you need way more sampling points than that. But this is the best we can do right now. And there were reports of debris making it from Lahaina into Lanai. And so we're just trying to establish, like what's kind of a baseline. And I think the goal would be to repeat it after a big rainstorm. And in that instance, you might even be able to get a better track of where it's drifting and try to track that. Yeah.
So, hey, thanks for your talk. It was really great. Appreciate it. And for kicking off the three of you, actually, thank you for kicking off our month or 3 weeks anyways of talks. Relative to this question and your answer, have you guys determined a reference site or kind of control that actually you could utilize as that baseline?
Yeah, so we are required to have control sites by our NSF grant. And our control sites are up here. So this is Ka'anapali, Kahikili, and this is Oluwalu. And so these are two very well studied sites that are outside of the burn zone. And so those are our control sites that we compare to for the reef metabolism and for the nearshore contaminants. And then this cluster of sites here, these are all inside the burn zone in Lahaina.
Okay, let's take 2 more questions. There's one over here, and then we'll take a question from Kilo.
Amazing talk. I love the reference. And I know you did a really interdisciplinary study for the water samples, and I think there's also, I've heard of this is the automated drone, the underwater drone that would take like a bunch of people around the country.
Ooh.
How does everyone collaborate and work for everyone that is interested in like getting that baseline condition before the big first rain brings all the off the water? So like, how are you putting yourself out there? How are you gonna? Has anyone reached out to you yet?
Yeah, so this is a really interesting question. So this is true. Somebody has taken an underwater drone all around this area, and aerial drones too. And there's all these organizations like EPA and Department of Health and various research groups and DAR and so many people. But luckily, West Maui is actually a very well coordinated area, thanks to mainly the efforts of Tova Calendar and Kim Felinsky, actually. And so they have weekly meetings where everybody meets and has a Zoom call and gives updates. And so I'm really hopeful for our ability to be able to share data across all these groups and across agencies. And it seems like everyone is just trying to collaborate and get an idea of what's going on. So yeah, stay tuned. Hopefully we get some sort of cohesive way to share all of that to the public.
Okay, and a question from Kilo.
Okay.
Yeah, in terms of thinking about resilience, has there been any attempt in either identifying or incorporating locals from Lahaina, high school students or grassroots organizations to come alongside of the boats and actually not just receive the data, but actually has there been an attempt to teach protocol so that they could attempt to replicate it way after when your NSF funding is done?
Yeah, I mean, so that's the hope. It hasn't happened yet. I mean, I've reached out to people that I knew who went to Lahaina Luna, and I think everybody's trying to work their networks, but it's really tough because that community in particular, I mean, they're under so much stress right now. It's not like a lot of people, I think, have the time to come and do this stuff. They have other more pressing issues. But so the leader of this project is Andrea Kealoha, and her whole family is from Maui. And she used to work at UH Maui College. And so I think we're trying to tap into UH Maui College and the students there and bring more people on to make sure that folks are involved in how we do this, because there is this huge demand for learning these skills and how to do all this stuff. It's honestly something that we aren't very good at in the state. So I think that's our hope. We're also, so Eileen Nally from Seaguy is working on looking at contaminants in fish. And so she's been in touch with local fishers who are going to be actually catching the fish and working with us to understand how contaminants are moving through that ecosystem. So yeah, that's certainly where we're trying to go.